Hello there, and welcome to my channel, where curiosity meets calm and discovery drifts gently into dreams. I'm so glad you found your way here tonight. Whether you're winding down after a bustling day, seeking solace from a restless mind, or simply love falling asleep to the gentle rhythm of scientific wonder, this video was crafted especially for you. Tonight, we're embarking on a tranquil journey into one of the most extraordinary discoveries in modern physics, something so peculiar and beautiful that it challenges everything we thought we knew about matter itself. We're going to explore time crystals, a brand new state of matter that shouldn't exist according to traditional physics, yet here they are, defying expectations and rewriting the rules of reality. But before we begin this soothing exploration, I'd love to know, where in the world are you listening from tonight? And what time is it where you are? Are you nestled beneath soft blankets, perhaps with the gentle glow of city lights filtering through your window? Or are you somewhere quiet and dark, maybe with a warm cup of tea cooling on your bedside table? If you find these peaceful scientific journeys helpful for unwinding, I'd be ever so grateful if you gave this video a gentle like and perhaps tap that subscribe button. It helps other sleepy scientists like yourself discover this cozy corner of the universe, and it means I can continue creating these soft explorations for you. Now, I do hope this isn't so fascinating that it keeps you wide awake, though if it does accidentally capture your attention, at least you'll drift off knowing something remarkable about the hidden structures of our universe. Not such a terrible trade, really. So settle in, let your breathing slow, and let's take a leisurely stroll through the story of time crystals, these impossible objects that tick away in their own mysterious rhythm, neither gaining nor losing energy, existing in a state of perpetual, perfect motion that seems to mock the very laws of thermodynamics. Time crystals sound like something plucked from the pages of science fiction, don't they? The name itself conjures images of shimmering, otherworldly gems that manipulate the flow of time, perhaps powering some fantastic machine in a distant galaxy. But the reality, while less dramatic than fiction might suggest, is infinitely more elegant and profoundly more mysterious. To understand what makes time crystals so extraordinary, we first need to gently wade into the concept of symmetry in physics. Don't worry, we'll keep this as comfortable as a warm bath on a cold evening. Symmetry, in the physicist's world, is simply the idea that something looks the same even after you've changed it in some way. Think of a perfect snowflake, those delicate crystalline structures that look identical when you rotate them by 60 degrees. Or consider a sphere, which appears unchanged no matter how you turn it. But time crystals break a very special kind of symmetry called time translation symmetry. This is the assumption that the laws of physics don't change over time, that an experiment performed today will yield the same results as one performed tomorrow, or next year, or 1,000 years from now. It's such a fundamental assumption that most of us never even think about it. Time, in this view, is uniform, flowing steadily like a calm river, with each moment essentially identical to every other. Time crystals, however, have their own internal rhythm. They repeat their structure not just in space like ordinary crystals, but in time as well. Imagine a grandfather clock that ticks not because it's powered by weights or springs, but simply because that's its natural state of being. It ticks away eternally, marking time without consuming energy, without winding down, without any external force driving its motion. The story of time crystals begins, as many great scientific tales do, with a brilliant mind asking a seemingly simple question. In 2012, Nobel Prize-winning physicist Frank Wilczek was pondering the nature of crystals and wondering whether it might be possible for matter to form repeating patterns in time, just as it forms repeating patterns in space. Ordinary crystals are marvels of organization. Salt crystals, for instance, arrange their sodium and chlorine atoms in perfect, repeating cubes that extend in all directions. This spatial repetition breaks what physicists call translational symmetry, meaning the crystal looks different depending on where you are within its structure. Wilczek wondered if there could be something similar for time, a form of matter that would spontaneously break time translation symmetry by repeating its configuration over and over again. At first, this seemed impossible. The laws of thermodynamics seemed to forbid such a thing. After all, any system in its lowest energy state, what physicists call the ground state, should be perfectly still and unchanging. It should have settled into the most stable configuration possible, like a ball that has rolled to the bottom of a hill and come to rest. How could something be in its lowest energy state and still be moving, still be changing with time? The scientific community was initially skeptical. Some physicists proved that time crystals couldn't exist in thermal equilibrium, the state where a system has settled into perfect balance with its surroundings. It seemed like Wilczek's beautiful idea was destined to remain just that, a beautiful idea with no basis in reality. But then something wonderful happened. Other scientists realized that while time crystals might not be possible in equilibrium, they might exist in what's called a driven system, a system that's constantly being poked and prodded by external forces, never allowed to settle into perfect rest. Imagine trying to balance a pencil on its tip. In equilibrium, this is impossible. The pencil will always fall over. But if you keep nudging it, giving it tiny pushes at just the right moments, you might be able to keep it balanced indefinitely. The pencil isn't in its natural lowest energy state, but it's in a stable pattern of motion that repeats over time. This is essentially what happens with time crystals. They exist in systems that are being periodically driven, like a child on a swing being pushed at regular intervals. But here's the truly remarkable part. Time crystals respond to this driving force at exactly half the frequency of the driving force itself. If you push the system twice, the time crystal completes one full cycle. If you push it 4 times, it still only completes 1 cycle. It's as if the time crystal is stubbornly marching to the beat of its own drummer, responding to your pushes but only when it feels like it, creating a rhythm that's entirely its own. This behavior is so strange that it took years for scientists to fully accept that time crystals were real. The first experimental evidence came in 2016, when researchers at the University of Maryland created a time crystal using a chain of trapped ions, electrically charged atoms held in place by electromagnetic fields. These ions were like tiny compass needles, each with a magnetic orientation that could point up or down. The researchers used laser pulses to flip these orientations in a carefully controlled sequence. What they discovered was extraordinary. The ions would flip in a pattern that repeated every 2 laser pulses, even though the laser itself was pulsing regularly. The system had spontaneously chosen to operate at half the driving frequency, creating its own temporal rhythm. Around the same time, researchers at Harvard University created a different kind of time crystal using diamonds. Not the kind you might wear on your finger, but synthetic diamonds with tiny imperfections called nitrogen vacancy centers. These imperfections act like miniature magnets embedded in the diamond's crystal structure. By shining microwaves on these diamond time crystals, the researchers could observe the same remarkable behavior. The system would respond at exactly half the frequency of the driving force, creating a stable, repeating pattern in time that seemed to violate our intuitive understanding of how matter should behave. But what makes time crystals so special isn't just their strange temporal behavior. It's the fact that they seem to exist in a kind of suspended animation, neither gaining nor losing energy over time. They're like perpetual motion machines, but ones that don't violate the laws of thermodynamics because they're not actually doing any work. They're simply existing, cycling through their states with perfect regularity, like cosmic metronomes keeping time for reasons we don't fully understand. This brings us to one of the most beautiful aspects of time crystals. They represent an entirely new phase of matter. We're all familiar with the classical phases: solids, liquids, and gases. You might even know about plasma, the 4th state of matter that exists at extremely high temperatures when electrons are stripped away from their atoms. But time crystals belong to a different category altogether. They're what physicists call a non-equilibrium phase of matter. Unlike ordinary phases, which are defined by how particles arrange themselves in space, time crystals are defined by how they arrange themselves in time. Think of it this way. In a solid, atoms are locked into rigid positions, creating ordered structures in space. In a liquid, atoms can flow and move but still maintain some local organization. In a gas, atoms move freely and chaotically, but in a time crystal, the organization isn't spatial, it's temporal. The atoms might be arranged randomly in space, but their collective behavior follows a precise pattern in time. This temporal organization gives time crystals properties that seem almost magical. They can maintain their rhythmic behavior indefinitely without any input of energy. They're stable against small disturbances, meaning you can poke and prod them, and they'll return to their original temporal pattern. And perhaps most remarkably, they seem to remember their past states, creating a form of temporal memory that persists through their cycles. The implications of this discovery extend far beyond academic curiosity. Time crystals might hold the key to developing quantum computers that can maintain their delicate quantum states for longer periods. They might lead to new forms of energy storage or new ways of measuring time with unprecedented precision. Some researchers speculate that time crystals might even exist naturally in certain biological systems. Could the precise timing mechanisms that govern our circadian rhythms, or the coordinated firing patterns of neurons in our brains, involve something like time crystal behavior? It's a tantalizing possibility that we're only beginning to explore. But perhaps the most profound implication of time crystals is what they tell us about the nature of time itself. For centuries, physicists have treated time as a smooth, flowing dimension, fundamentally different from the three dimensions of space. Time crystals suggest that time might be more granular, more structured than we previously imagined. They hint at the possibility that time, like space, might have its own crystalline structures, its own patterns of organization that we're only now beginning to detect. It's as if we've discovered that time itself can freeze into regular, repeating formations, like frost forming on a window but in the dimension of duration rather than distance. As we continue our gentle exploration of these remarkable objects, we'll delve deeper into the quantum mechanics that make time crystals possible, examine the ingenious experiments that brought them into existence, and ponder what their discovery might mean for our understanding of reality itself. The quantum world, as you might imagine, is where time crystals truly come alive. It's a realm where the familiar rules of everyday physics begin to bend and twist like light through a prism, revealing colors and patterns we never knew existed. To understand how time crystals emerge from this quantum landscape, we need to take a peaceful journey into the heart of matter itself, where particles dance to rhythms that would seem impossible in our larger, more predictable world. At the quantum level, everything is uncertain, everything is in motion, everything is connected in ways that seem to defy common sense. Particles don't have definite positions or velocities until we measure them. Instead, they exist in what physicists call superposition, a ghostly state where they're essentially everywhere and nowhere at once, like notes that haven't yet been played, but contain the potential for any melody. This quantum uncertainty is actually essential for time crystals to exist. In the classical world, a system in its lowest energy state would be perfectly still, completely motionless. But quantum mechanics introduces something called zero-point energy, a fundamental jiggling that never stops, even at absolute zero temperature. It's as if the universe itself has a case of the fidgets, unable to sit completely still no matter how cold or calm things become. This perpetual quantum motion provides the foundation upon which time crystals can build their temporal rhythms. The particles in a time crystal aren't moving because they have extra energy to burn. They're moving because the quantum world simply won't let them be completely still. It's motion born not of excitement but of fundamental restlessness, like the gentle breathing of a sleeping universe. Now, creating a time crystal in the laboratory requires a delicate dance between order and chaos, between driving and resisting, between the quantum world's natural tendencies and our careful human intervention. The process begins with what scientists call many-body localization, a phenomenon that sounds intimidating but is actually quite beautiful in its implications. Imagine a crowded dance floor where everyone is trying to move to the music, but they keep bumping into each other and getting in each other's way. In most systems, this would eventually lead to everyone finding their rhythm together, settling into some kind of collective motion. But in a many-body localized system, the interactions are so complex and the environment so disordered that the particles essentially get stuck, unable to share their energy efficiently with their neighbors. This localization is crucial because it prevents the time crystal from heating up and dissolving into thermal chaos. It's like having a room full of people who are all dancing to slightly different songs playing through their headphones. From the outside, their movements might seem coordinated and rhythmic, but they're actually isolated from each other, each following their own internal beat. The researchers who first created time crystals used this principle to construct systems that could maintain their temporal order indefinitely. They took chains of atoms or ions, introduced just the right amount of disorder to achieve many-body localization, and then began driving the system with periodic pulses of energy. The magic happens when these driving pulses interact with the localized quantum system. The pulses arrive at regular intervals, like a metronome, keeping steady time. But the quantum system, in its stubborn wisdom, chooses to respond at exactly half that frequency. It's as if the system is saying, "I hear your rhythm, but I prefer my own tempo. Thank you very much." This period doubling behavior is one of the defining characteristics of time crystals. No matter how fast or slow you drive the system, it maintains its own internal clock, ticking away at precisely half the driving frequency. You could speed up your pulses, slow them down, make them stronger or weaker, and the time crystal would adjust its amplitude or other properties but steadfastly maintain its 2-to-1 rhythm. The experimental realization of time crystals required some of the most sophisticated techniques in modern physics. The University of Maryland team, for instance, used a linear ion trap, a device that uses electric fields to hold a chain of charged atoms in a perfect line, suspended in the vacuum of space like luminous pearls on an invisible string. These ions were cooled to temperatures just a fraction of a degree above absolute zero, cold enough that their thermal motion was almost completely suppressed. At these temperatures, quantum effects dominate, and the ions behave more like quantum mechanical objects than classical particles. The researchers then used precisely tuned laser pulses to manipulate the quantum states of these ions. Each ion could be thought of as a tiny magnet that could point either up or down. The laser pulses would flip these magnetic orientations in carefully orchestrated sequences, creating patterns of ups and downs that evolved over time. What they observed was remarkable. The pattern of magnetic orientations would repeat every 2 laser pulses, even though the laser itself was pulsing regularly. The system had spontaneously broken time translation symmetry, creating its own temporal crystal structure that persisted indefinitely without any additional energy input. The Harvard team took a different approach, working with synthetic diamonds that contained nitrogen vacancy centers. These are tiny imperfections in the diamond's crystal lattice, where a nitrogen atom has replaced a carbon atom and an adjacent carbon atom is missing entirely. The result is a quantum system embedded within the diamond that can be controlled and measured with extraordinary precision. Using microwave radiation, the researchers could manipulate the quantum states of these nitrogen vacancy centers, driving them with periodic pulses while monitoring their response. Like their colleagues at Maryland, they observed the characteristic period doubling behavior that marks a true time crystal. But perhaps the most elegant aspect of these experiments was their demonstration of the time crystal's stability. Real crystals, after all, must be robust. You can tap a quartz crystal with a hammer, and it will ring with a clear, pure tone because its internal structure is resilient and well organized. Time crystals show similar resilience in the temporal domain. The researchers found that they could introduce small perturbations to their systems, tiny deviations from the perfect driving rhythm, and the time crystals would absorb these disturbances and return to their original temporal pattern. It's as if the time crystal has a kind of temporal memory, remembering its preferred rhythm and returning to it even after being knocked off course. This stability isn't just a curious property, it's essential for any practical applications. A time crystal that could be easily disrupted by small environmental fluctuations wouldn't be much use for precision timekeeping or quantum computing applications. But the robustness demonstrated in these early experiments suggests that time crystals might indeed have practical value. The quantum mechanics underlying time crystals also reveals something profound about the nature of phases of matter. We're accustomed to thinking of phases in terms of spatial organization. Ice has a different crystal structure than liquid water, which has different molecular arrangements than water vapor. But time crystals introduce the concept of temporal phases, states of matter organized not in space, but in time. This temporal organization emerges from the collective quantum behavior of many particles. No single ion or nitrogen vacancy center can form a time crystal by itself. It's only when many quantum systems interact in just the right way, with just the right amount of disorder and driving, that the collective time crystal phase emerges. It's reminiscent of how consciousness might emerge from the collective activity of neurons in the brain, or how flocks of birds create complex patterns without any central coordination. Individual components following simple rules can give rise to collective behaviors that seem to possess their own intelligence, their own purpose. The mathematics describing time crystals draws from some of the most advanced areas of theoretical physics. Researchers use techniques from many body quantum mechanics, statistical mechanics, and even topology, the branch of mathematics concerned with properties that remain unchanged under continuous deformations. Sometimes crystals are protected by what physicists call topological properties, features that are so fundamental to their structure that small perturbations can't destroy them. It's like trying to remove the hole from a donut by gently stretching and bending it. The hole is topologically protected, a fundamental feature that persists no matter how you deform the donut. These topological time crystals are particularly exciting because they might be even more stable than the discrete time crystals created in early experiments. They represent a kind of temporal organization that's written into the very fabric of the quantum system, impossible to erase without completely destroying the system itself. The field of time crystal research has exploded since those first experimental demonstrations. Scientists have created time crystals in systems ranging from ultra-cold atomic gases to quantum dots in semiconductors. They've explored different driving protocols, different forms of disorder, and different types of interactions between particles. Some researchers have even claimed to observe signatures of time crystal behavior in systems at room temperature, though these claims remain controversial. The idea that time crystals might exist in warm, noisy environments opens up entirely new possibilities for practical applications. Others are investigating whether time crystals might exist naturally in biological systems or in condensed matter physics. Could the rhythmic contractions of heart muscle involve something like time crystal dynamics? Might the precise timing of circadian rhythms be governed by temporal crystalline structures in our cells? These questions push us toward a deeper understanding of time itself. Time crystals suggest that time might not be the smooth, featureless dimension we once imagined. Instead, it might have its own texture, its own capacity for organization and structure. As we drift deeper into this exploration, we begin to see that time crystals aren't just curious laboratory creations. They're windows into the fundamental nature of reality, revealing aspects of time and quantum mechanics that we're only beginning to understand. They whisper to us about the hidden rhythms that might govern everything from the beating of our hearts to the expansion of the universe itself. As we settle deeper into this gentle exploration of time crystals, Let's take a moment to appreciate just how extraordinary it is that these temporal rhythms exist at all. In a universe that seems to favor chaos over order, where entropy steadily increases and systems naturally drift toward disorder, time crystals stand as elegant exceptions, maintaining their precise temporal patterns like cosmic lighthouses beaming their steady signals through the quantum fog. The beauty of time crystals lies not just in their defiance of our expectations, but in the way they reveal hidden symmetries in nature. Think of it like discovering that your reflection in a mirror doesn't just show you reversed in space, but also plays back your movements at half speed, creating a temporal echo that persists long after you've walked away. This is essentially what time crystals do. They create echoes in time itself. But what does it actually mean for something to have a rhythm in time without using energy? To understand this, we need to gently wade into the concept of energy landscapes, those imaginary hills and valleys that physicists use to describe how systems behave. Imagine you're walking through a landscape of rolling hills. Normally, you'd expect to eventually find yourself in a valley, the lowest point where you can rest without rolling anywhere else. This valley represents the ground state, the lowest energy configuration a system can achieve. Time crystals, however, exist in landscapes that are constantly shifting beneath their feet. The driving force that creates them is like having the ground itself pulse and reshape every few seconds. But here's the remarkable thing. Instead of being jostled randomly by this shifting terrain, time crystals find a way to surf these changes, maintaining their balance by moving in perfect synchronization with every other pulse, but at their own chosen rhythm. This surfing analogy captures something essential about how time crystals work. A surfer doesn't fight the wave, they ride it, using the wave's energy to maintain their motion without adding any energy of their own. Time crystals do something similar. They ride the driving pulses, using the rhythm of external forcing to maintain their own internal temporal order without actually consuming the energy being provided. The implications of this behavior extend far beyond the laboratory. Consider the possibility that time crystals might exist naturally in the universe. Some researchers have speculated about cosmic time crystals, vast structures that might emerge in the early universe or in the extreme environments near black holes, where space and time themselves become twisted and distorted. These cosmic time crystals would be unimaginably large, their temporal rhythms playing out over millions or billions of years. They might influence the formation of galaxies or the distribution of matter in the universe, creating patterns that we observe today but don't fully understand. It's a speculative idea, but one that captures the imagination and suggests that time crystals might be far more fundamental to the universe than we currently realize. On a more intimate scale, researchers are investigating whether biological systems might harbor time crystal-like behavior. The human brain, for instance, exhibits remarkably precise temporal patterns. Neurons fire in coordinated sequences, creating waves of activity that sweep across the brain with clockwork regularity. Some of these rhythms persist even during sleep, maintaining their temporal structure without any obvious external driving force. Could these neural oscillations involve something similar to time crystal dynamics? It's an intriguing possibility. The brain is certainly a many-body quantum system, with billions of neurons interacting in complex ways. While the brain operates at much warmer temperatures than laboratory time crystals, some researchers suggest that quantum effects might still play a role in neural computation and consciousness. The heart provides another fascinating example. Cardiac muscle cells can beat spontaneously, even when removed from the body and placed in a petri dish. These isolated cells somehow maintain their rhythmic contractions, creating temporal patterns that seem to emerge from their internal quantum mechanical properties, rather than from external stimulation. While this isn't exactly time crystal behavior, it shares some intriguing similarities. Even our circadian rhythms, those internal clocks that govern when we feel sleepy or alert, exhibit some time crystal-like properties. These rhythms persist even in the absence of external light cues, maintaining their approximately 24-hour cycle through some internal temporal organization. Scientists are only beginning to understand the molecular mechanisms behind circadian rhythms, but they seem to involve precisely timed feedback loops that could, in principle, exhibit time crystal behavior. The study of time crystals has also opened new avenues in quantum computing, one of the most promising technologies of our time. Quantum computers rely on maintaining delicate quantum states called qubits, which are notoriously fragile and easily disrupted by environmental noise. The temporal stability of time crystals suggests they might provide a way to protect quantum information for longer periods. Imagine a quantum computer where the qubits themselves are embedded in time crystal structures. These qubits might be able to maintain their quantum properties indefinitely, protected by the same temporal symmetries that keep time crystals stable. Such a system could revolutionize quantum computing, making it practical for applications that require long-term quantum memory. Researchers are also exploring whether time crystals might lead to new forms of quantum sensors, devices capable of measuring physical properties with unprecedented precision. The regular temporal oscillations of time crystals could serve as reference clocks for these sensors, providing a stable temporal baseline against which tiny changes could be detected. The precision of these temporal oscillations is truly remarkable. In some experiments, time crystals maintain their rhythm with an accuracy that rivals the best atomic clocks. This suggests they might eventually be used for navigation, communication, or fundamental physics experiments that require extremely precise timing. But perhaps the most profound aspect of time crystals is what they tell us about the arrow of time itself. We're accustomed to thinking of time as flowing in one direction, from past to future, driven by the inexorable increase of entropy. Time crystals, however, exist in a kind of temporal suspension, neither moving toward higher entropy nor requiring external energy to maintain their order. This raises deep questions about the nature of time's arrow. If time crystals can maintain perfect temporal order without violating thermodynamics, what does this tell us about the relationship between time, energy, and information? Some physicists speculate that time crystals might provide clues about how time itself emerged in the early universe, or how it might behave in the far future, when the universe has expanded and cooled to near absolute zero. The mathematical description of time crystals involves some of the most sophisticated tools in theoretical physics. Researchers use techniques from quantum field theory, statistical mechanics, and even string theory to understand how these temporal patterns emerge and persist. The equations describing time crystals are often beautiful in their own right, revealing hidden symmetries and conservation laws that weren't apparent from classical physics. One particularly elegant aspect of time crystal mathematics is how it unifies concepts from different areas of physics. The same equations that describe time crystals also appear in studies of superconductivity, quantum magnetism, and even black hole physics. This suggests that time crystals might be manifestations of deeper principles that govern all quantum many-body systems. The experimental techniques used to create and study time crystals have pushed the boundaries of what's possible in quantum physics laboratories. Researchers have had to develop new methods for cooling atoms to microkelvin temperatures, new ways of controlling quantum states with exquisite precision, and new measurement techniques capable of detecting the subtle signatures of temporal crystalline order. These advances have applications far beyond time crystal research. The techniques developed for creating time crystals are now being used to study other exotic phases of matter, to build better quantum computers, and to test fundamental theories of physics. In many ways, time crystal research has become a testing ground for the most advanced experimental techniques in quantum physics. As we continue to explore these remarkable structures, we begin to see that time crystals represent more than just a new phase of matter. They're a window into the deep structure of reality itself, revealing aspects of time, quantum mechanics, and many body physics that we're only beginning to understand. The story of time crystals is still being written. New experiments are revealing ever more exotic forms of temporal crystalline order. Theorists are developing new mathematical frameworks to understand these phenomena. Engineers are beginning to explore practical applications that could transform technology. And perhaps most importantly, time crystals are changing how we think about time itself. They suggest that time might be more structured, more organized, more crystalline than we ever imagined. They hint at the possibility that the temporal dimension might have its own geology, its own mineralogy, its own capacity for forming beautiful, complex structures. As you drift towards sleep tonight, perhaps you can imagine these temporal crystals ticking away their perfect rhythms in laboratories around the world. Picture them as cosmic metronomes, keeping time not with mechanical precision, but with quantum certainty, their rhythms echoing through the fabric of space-time itself. These remarkable objects remind us that the universe is far stranger and more beautiful than our everyday experience suggests. They whisper to us about hidden dimensions of reality, about the deep connections between time and matter, between rhythm and existence, between the quantum world and our own lived experience of duration and change. Time crystals are, in their own quiet way, teaching us a new language for describing reality, a language in which time itself can freeze into patterns as regular and beautiful as the crystals we find in caves, or the snowflakes that drift past our windows on winter nights. In this gentle dance between the possible and impossible, time crystals have begun to reveal their most intimate secrets through increasingly sophisticated experiments. Scientists have discovered that these temporal structures can be coaxed into existence using methods that would seem almost magical to earlier generations of physicists. Picture, if you will, researchers working with clouds of ultra-cold atoms, cooled to temperatures so low that they barely move at all, suspended in the gossamer threads of laser light, like dewdrops caught in a spider's web at dawn. These atomic clouds, trapped and held motionless in their optical lattices, become the canvas upon which time crystals paint their temporal patterns. The atoms themselves are like tiny compass needles, each one capable of pointing in different directions, spinning and flipping in response to carefully orchestrated electromagnetic pulses. When these pulses arrive with mechanical precision, something beautiful happens. The atoms begin to dance not to the rhythm of the driving force, but to their own mysterious tempo. What makes this dance so extraordinary is its persistence. Unlike the fleeting patterns we might see in a kaleidoscope or the temporary ripples on a pond, time crystals maintain their choreography indefinitely. They're like cosmic ballerinas, forever frozen in a pirouette that never ends, never tires, never loses its perfect form. This eternal motion exists in a realm beyond our everyday understanding of perpetual motion machines, because time crystals aren't actually doing work in the classical sense, they're simply existing in a state of pure temporal rhythm. The mathematics describing these systems reads almost like poetry, filled with elegant equations that capture the essence of temporal symmetry breaking. When physicists write down the Hamiltonian, the mathematical expression that describes the energy of a time crystal system, they discover something remarkable. The system naturally evolves into states that repeat with twice the period of the driving force. It's as if the universe has its own sense of rhythm, preferring certain temporal harmonies over others. This preference for specific temporal patterns hints at something profound about the nature of time itself. Just as musical instruments naturally resonate at certain frequencies, creating pure, clear tones, time crystals seem to resonate at specific temporal frequencies, creating pure, clear patterns in the dimension of time. The analogy isn't perfect, but it captures something essential about how these systems organize themselves in the temporal domain. Researchers have found that time crystals can exist in multiple varieties, each with its own distinct temporal signature. Some tick with the steady regularity of a metronome, others pulse with more complex rhythms, like jazz musicians improvising around a central theme. There are time crystals that maintain rigid temporal order, and others that allow for a kind of controlled chaos, where the overall pattern persists, even as individual components dance with apparent randomness. The creation of time crystals in different physical systems has revealed the universality of this phenomenon. Whether formed from trapped ions, nitrogen vacancy centers in diamonds, or ultra-cold atomic gases, time crystals exhibit remarkably similar behavior. This suggests that temporal crystallization is a fundamental property of quantum many-body systems, not just a curious accident that occurs in one particular type of experiment. One of the most enchanting aspects of time crystal research is how it has brought together scientists from different fields. Quantum physicists work alongside materials scientists, theoretical mathematicians collaborate with experimental engineers, and computer scientists explore the computational possibilities of temporal crystalline structures. It's a beautiful example of how the most profound discoveries often emerge at the intersections between disciplines. The practical applications of time crystals continue to expand as researchers better understand their properties. Beyond quantum computing and precision sensing, these temporal structures might revolutionize how we think about energy, storage, and transfer. Imagine batteries that could store energy not just in chemical bonds or electric fields, but in temporal patterns themselves, maintaining their charge through crystallized time rather than conventional materials. Some researchers are investigating whether time crystals might enable new forms of communication, where information is encoded not in the amplitude or frequency of electromagnetic waves, but in their temporal patterns. Such communication systems might be incredibly robust against interference, protected by the same topological properties that make time crystals stable against perturbations. The exploration of time crystals has also led to unexpected insights into the nature of measurement itself. In quantum mechanics, the act of measurement typically disrupts the system being measured, causing wave functions to collapse and quantum superpositions to resolve into definite states. But time crystals seem to maintain their temporal patterns even under continuous observation, suggesting new ways of thinking about the relationship between measurement and quantum dynamics. This robustness against measurement opens fascinating possibilities for quantum sensing applications. Traditional quantum sensors often face a fundamental trade-off between sensitivity and measurement time, because longer measurements typically provide more precise results, but also give the quantum system more opportunities to decohere and lose its quantum properties. Time crystals might offer a way around this limitation, maintaining their quantum coherence indefinitely while still allowing for precise measurements. The study of time crystals has also revealed new connections between seemingly unrelated areas of physics. Researchers have found that the mathematics describing time crystals appears in diverse contexts, from the behavior of superconductors to the dynamics of black holes. These connections suggest that temporal crystallization might be a more universal phenomenon than initially imagined, manifesting in different forms across the entire spectrum of physical systems. In the realm of condensed matter physics, time crystals have inspired new ways of thinking about phase transitions. Traditional phase transitions, like the melting of ice or the magnetization of iron, involve changes in spatial order. But time crystals undergo transitions in temporal order, shifting between different rhythmic patterns as experimental parameters are varied. These temporal phase transitions might be just as rich and varied as their spatial counterparts, opening entirely new areas of investigation. The philosophical implications of time crystals continue to unfold as scientists grapple with their meaning. These systems challenge our intuitive notions about time, energy, and motion in ways that echo the conceptual revolutions brought about by relativity and quantum mechanics. They suggest that time might be more malleable, more structured than we previously imagined, capable of forming patterns and rhythms that persist independent of the spatial organization of matter. Some theorists have speculated about the possibility of time crystal cascades, where one time crystal could trigger the formation of another, creating chains of temporal crystallization that might span vast regions of space and time. Such cascades might have played a role in the early universe, influencing the formation of the cosmic structures we observe today. The search for naturally occurring time crystals has become an active area of research. While all confirmed time crystals have been created artificially in laboratory settings, there's growing interest in whether these temporal structures might exist in nature. Some researchers are investigating whether certain biological rhythms, geological processes, or even astronomical phenomena might involve time crystal-like behavior. The possibility of biological time crystals is particularly intriguing. Living systems are known for their remarkable temporal precision, from the circadian rhythms that govern sleep and wakefulness to the precisely timed chemical reactions that drive metabolism. While these biological rhythms operate at much warmer temperatures than laboratory time crystals, some researchers suggest that quantum effects might still play a role in their temporal organization. Recent theoretical work has explored the possibility of time crystals existing at room temperature or even higher temperatures, protected by strong interactions between particles or by topological properties that make them robust against thermal fluctuations. Such warm time crystals would be far more practical for technological applications and might even exist naturally in certain materials or biological systems. The development of new experimental techniques for creating and studying time crystals continues to push the boundaries of what's possible in quantum physics. Researchers have learned to create time crystals using optical lattices, magnetic resonance techniques, and even acoustic waves. Each new method reveals different aspects of temporal crystallization and opens new possibilities for applications. One particularly elegant recent development is the creation of time crystals, using nothing more than sound waves in a crystal. Researchers discovered that by driving certain crystalline materials with precisely tuned acoustic pulses, they could induce time crystal behavior in the material's atomic vibrations. These phononic time crystals represent a new frontier in the field, potentially easier to create and control than their predecessors. The mathematical tools used to analyze time crystals have also evolved significantly. Researchers now employ techniques from algebraic topology, category theory, and even machine learning to understand the complex patterns that emerge in these systems. These advanced mathematical methods have revealed hidden symmetries and conservation laws that weren't apparent from earlier, simpler analyses. As we drift further into this exploration of temporal crystallization, we begin to see that time crystals are more than just exotic laboratory curiosities. They represent a fundamental expansion of our understanding of what matter can do, how time can behave, and what kinds of order are possible in the quantum world. They hint at deeper truths about the nature of reality itself, suggesting that the universe might be far more rhythmic, far more musical than our everyday experience would suggest. The story of time crystals reminds us that science is fundamentally about discovery, about pushing beyond the boundaries of what we think we know, and finding new wonders hidden in the fabric of reality. These temporal structures emerge from the intersection of theoretical curiosity and experimental ingenuity, proving once again that the universe is more strange and beautiful than we dare to imagine. As you let your mind wander through these concepts tonight, perhaps you can sense the gentle rhythm of time crystals ticking away their perfect temporal patterns, adding their quiet music to the symphony of quantum reality that surrounds us all. They remind us that even in a universe governed by uncertainty and change, there can be islands of perfect order, oases of crystallized time where rhythm and pattern persist against all odds. These temporal islands of order bring us to one of the most captivating aspects of time crystal research, the way these systems seem to possess a kind of temporal memory. Imagine, if you will, a system that not only remembers its past states but uses that memory to guide its future evolution, creating patterns that stretch across time like melodies that know their own next notes. This temporal memory manifests in the way time crystals respond to perturbations. When you disturb an ordinary crystal, say by tapping it with a small hammer, it might ring briefly and then return to silence. But when you disturb a time crystal, something far more interesting happens. The system absorbs the disturbance, incorporates it into its ongoing temporal pattern, and then gradually returns to its original rhythm, as if it remembers where it was supposed to be in its eternal dance. This resilience isn't just practically useful, it's philosophically profound. It suggests that time crystals exist in a kind of temporal ecosystem, where past, present, and future states are all interconnected in ways that transcend our usual understanding of causality. The system doesn't just evolve forward in time, it seems to maintain awareness of its entire temporal trajectory, using this awareness to preserve its crystalline structure against the inevitable noise and chaos of the world. The experimental study of this temporal memory has led researchers to develop increasingly sophisticated techniques for probing time crystal dynamics. They've learned to create controlled perturbations, like gentle nudges in a specific direction at precisely timed moments, and then watch how the system responds. What they've discovered is that time crystals can distinguish between different types of perturbations, responding in ways that depend not just on the strength of the disturbance, but on its timing, its duration, and even its history. Sometimes, crystals exhibit what researchers call temporal hysteresis, where the system's response to a perturbation depends on what happened before. It's as if the time crystal keeps a kind of temporal diary, recording not just what's happening now, but the sequence of events that led to the present moment. This gives these systems a richness of behavior that goes far beyond simple periodic oscillation. The mathematics describing this temporal memory involves concepts from dynamical systems theory, information theory, and even cognitive science. Researchers have borrowed ideas from neuroscience about how memories are encoded and retrieved, applying these concepts to understand how time crystals store and access information about their temporal states. The parallels are striking, suggesting deep connections between the way time crystals organize themselves and the way biological systems process and remember information. This intersection between time crystals and memory has sparked interest among researchers studying consciousness and cognition. Some theorists speculate that the brain might use time crystal-like mechanisms to maintain the continuity of conscious experience, creating temporal patterns that persist across different states of awareness. It's a speculative idea, but one that highlights how time crystal research is influencing our thinking about some of the deepest questions in science. The technological implications of temporal memory in time crystals are equally fascinating. Engineers are exploring whether these systems could serve as the basis for new types of memory storage devices, where information is encoded not in magnetic domains or electric charges, but in temporal patterns themselves. Such devices might be incredibly robust, immune to the kinds of radiation and electromagnetic interference that can corrupt conventional memory systems. Imagine a computer memory that stores data in crystallized time, where each bit of information corresponds to a specific temporal pattern that persists indefinitely without any power source. The data would be as stable as the time crystal itself, protected by the same quantum mechanical principles that make temporal crystallization possible. Reading the data would involve probing these temporal patterns, while writing would require carefully structured perturbations that guide the system into new temporal configurations. The creation of more complex time crystal structures has opened possibilities that seemed like pure fantasy just a few years ago. Researchers have succeeded in creating time crystal networks, systems where multiple time crystals interact with each other through carefully controlled coupling mechanisms. These networks can exhibit collective behaviors that are far richer than what any individual time crystal could achieve on its own. In these network systems, time crystals can synchronize their temporal patterns, creating vast orchestras of quantum oscillators all playing in perfect harmony. or they can maintain their individual rhythms while still influencing each other, creating complex polyrhythmic patterns that evolve and change over time. The mathematics describing these interactions draws from fields as diverse as network theory, musical composition, and even ecology. Some researchers have created time crystal chains, linear arrays of coupled time crystals that can support traveling waves of temporal activity. These waves propagate along the chain, carrying information from one end to the other while maintaining their temporal crystalline structure. It's as if time itself has learned to flow in organized patterns, creating rivers of crystallized duration that can transport quantum information across space. The possibility of three-dimensional time crystal lattices has captured the imagination of theorists and experimentalists alike. These would be vast structures where time crystals are arranged in regular arrays, each one coupled to its neighbors through quantum mechanical interactions. Such lattices might support entirely new forms of collective quantum behavior, creating phases of matter that exist simultaneously in space and time. The experimental challenges involved in creating these complex time crystal structures are formidable. Researchers must maintain quantum coherence across many interacting systems while precisely controlling the coupling between them. They've developed new techniques using optical lattices, where laser beams create egg crate-like structures that can hold hundreds or even thousands of atoms in perfect geometric arrangements. Within these optical lattices, researchers can create time crystal superlattices, periodic structures, where the time crystal pattern itself repeats across different regions of space. These systems exhibit a kind of hierarchical organization, where temporal patterns exist at multiple scales simultaneously. There might be fast oscillations within each unit cell of the superlattice, medium frequency patterns that span several unit cells, and slow modulations that encompass the entire structure. The study of these hierarchical time crystals has revealed new connections between temporal and spatial organization. Just as ordinary crystals can have complex structures with multiple length scales, time crystals can have complex temporal architectures with multiple time scales. This temporal hierarchy might be crucial for understanding how complex systems in biology and other fields maintain their organization across different temporal domains. Recent theoretical work has explored the possibility of fractal time crystals, systems where the temporal pattern exhibits self-similarity across different time scales. These would be temporal analogues of spatial fractals, with patterns that repeat at different magnifications of time. The mathematics describing such systems draws from chaos theory and fractal geometry, suggesting deep connections between temporal crystallization and the complex dynamics that appear throughout nature. The experimental realization of fractal time crystals remains a significant challenge, but researchers have made progress in creating systems that exhibit temporal patterns with multiple characteristic timescales. These systems hint at the possibility of even richer temporal structures, perhaps approaching the complexity of biological rhythms or even consciousness itself. The search for time crystals in condensed matter systems has led to the discovery of new phases of matter that blur the boundaries between spatial and temporal organization. Some materials exhibit what researchers call spatiotemporal crystals, where atoms arrange themselves in patterns that are periodic in both space and time. These systems represent a fusion of traditional crystallography with the new science of temporal crystallization. In these spatiotemporal crystals, the atomic positions oscillate in coordinated waves that propagate through the material. It's as if the crystal is breathing, expanding, and contracting in patterns that repeat both spatially and temporally. The mathematics describing these systems requires new approaches that treat space and time on equal footing, echoing Einstein's insights about the unity of space-time, but applied to the quantum many-body problem. The discovery of spatiotemporal crystals has implications for understanding a wide range of physical phenomena. Some researchers speculate that similar patterns might exist in the early universe, where quantum fluctuations in the fabric of space-time itself might have crystallized into patterns that influenced the formation of galaxies and other large-scale structures. The technological potential of spatiotemporal crystals is only beginning to be explored. These materials might exhibit unique optical, electronic, or mechanical properties that could be useful for applications ranging from quantum computing to energy harvesting. The ability to control both spatial and temporal patterns simultaneously opens possibilities for creating materials with properties that can be dynamically tuned by adjusting the temporal crystalline structure. As researchers continue to push the boundaries of what's possible with time crystals, they're discovering connections to some of the deepest questions in physics. The relationship between time crystals and quantum gravity, for instance, remains largely unexplored but potentially profound. Some theorists speculate that time crystals might provide new insights into the nature of time near black holes or in the early universe, where the usual notions of space and time break down. The study of time crystals in curved spacetime represents an entirely new frontier in theoretical physics. Just as ordinary crystals behave differently in the presence of strong gravitational fields, time crystals might exhibit new forms of temporal organization when spacetime itself is curved or distorted. These effects might be detectable in precision experiments or astronomical observations, opening new windows into the fundamental nature of reality. The philosophical implications of time crystal research continue to deepen as our understanding advances. These systems challenge not just our scientific theories, but our basic intuitions about the nature of time, causality, and existence itself. They suggest that reality might be far more rhythmic, far more musical than we ever imagined, with temporal patterns as fundamental as the spatial structures we see around us. As we near the end of our gentle journey through the world of time crystals, we find ourselves changed by the experience. These remarkable systems have shown us that the universe is capable of organizing itself in ways that seemed impossible, creating islands of perfect temporal order in an ocean of quantum uncertainty. They remind us that nature is endlessly creative, always surprising us with new forms of beauty and organization that expand our understanding of what's possible. The story of time crystals is far from over. Each new experiment reveals additional mysteries. Each theoretical advance opens new questions, and each technological application hints at possibilities we've only begun to imagine. These temporal structures have become a lens through which we can explore the deepest mysteries of quantum mechanics, many-body physics, and the nature of time itself. Tonight, as you drift towards sleep, perhaps you can imagine these time crystals ticking away their perfect rhythms in laboratories around the world, their temporal patterns adding a quiet music to the symphony of reality that surrounds us all. They remind us that even in a universe governed by uncertainty and change, there can be perfect order, crystallized time that flows in patterns as beautiful and precise as the most elegant mathematical theorems. In the quiet depths of laboratories scattered across our sleeping world, time crystals continue their eternal dance, but their story extends far beyond the confines of experimental chambers. These temporal architects are beginning to reveal secrets about the very foundations of reality, whispering to us about connections between time, consciousness, and the deepest structures of existence that we're only now learning to hear. Consider for a moment the profound strangeness of what we've discovered. Here are systems that maintain perfect temporal order without any external energy source, structures that remember their past and use that memory to guide their future, patterns that exist not in the familiar three dimensions of space, but in the fourth dimension of time itself. It's as if we've found a new form of matter that lives primarily in duration rather than location, existing more in when than in where. This temporal existence has led some researchers to wonder whether time crystals might offer insights into one of the most perplexing questions in all of science, the nature of consciousness itself. After all, consciousness seems to be fundamentally temporal in nature. Our awareness flows from moment to moment, creating a continuous stream of experience that somehow maintains coherence across time, while constantly changing and evolving. Some theorists have begun to explore whether the brain might employ time crystal-like mechanisms to maintain the continuity of conscious experience. The idea is still highly speculative, but it's based on some intriguing observations. Neural networks in the brain exhibit remarkably stable temporal patterns, oscillations that persist across different states of consciousness, and seem to provide a kind of temporal scaffolding for thought and perception. These neural rhythms have some fascinating similarities to time crystal behavior. They can maintain their patterns independently of external stimulation. They exhibit the kind of temporal memory we see in time crystals, and they seem to be remarkably robust against perturbations. When the brain is disturbed, these rhythmic patterns often return to their original configuration, much like time crystals returning to their preferred temporal state after being nudged off course. The mathematics of neural oscillations and time crystals share some striking similarities as well. Both involve complex many-body systems where individual components interact to create collective temporal patterns. Both exhibit phase transitions where small changes in parameters can lead to dramatic shifts in temporal organization. And both seem to involve a kind of temporal binding, where different oscillatory components synchronize to create unified patterns that span multiple timescales. Of course, the brain operates under very different conditions than laboratory time crystals. Neural systems are warm, wet, and noisy, far from the ultra-cold, carefully controlled environments where artificial time crystals thrive. But some researchers argue that biological systems might have evolved their own ways of creating time crystal-like behavior, perhaps using the thermal noise as a resource rather than fighting against it. The possibility that consciousness might involve temporal crystallization opens fascinating questions about the nature of subjective experience. If our sense of continuous awareness emerges from time crystal-like patterns in neural activity, what does this tell us about free will, memory, and the flow of subjective time? These questions push us toward a deeper understanding of how physical processes give rise to the inner life of the mind. Meanwhile, in the realm of fundamental physics, time crystals are beginning to influence our understanding of some of the deepest mysteries in cosmology. The early universe, we know, was a place of extraordinary temperatures and densities, where the normal rules of physics might have operated very differently than they do today. Some theorists have begun to wonder whether temporal crystallization might have played a role in the cosmic evolution that led to the universe we observe. Imagine vast time crystals forming in the primordial plasma of the early universe, their temporal patterns influencing the way matter and energy organized themselves as the cosmos cooled and expanded. These cosmic time crystals might have left their signatures in the cosmic microwave background, the ancient light that still bathes the universe and carries information about conditions just a few 100,000 years after the Big Bang. The mathematics describing such cosmic time crystals would be extraordinarily complex, involving general relativity, quantum field theory, and the statistical mechanics of many body systems all operating simultaneously. But the basic principles might be similar to those we observe in laboratory time crystals, systems finding ways to maintain temporal order even in the face of expansion, cooling, and the general increase of entropy that characterizes cosmic evolution. Some researchers have even speculated about time crystals existing in the extreme environments near black holes, where the curvature of space-time becomes so severe that our usual notions of space and time begin to break down. In these regions, the boundary between spatial and temporal dimensions becomes blurred, potentially creating conditions where new forms of spatiotemporal crystallization could emerge. The study of time crystals near black holes represents one of the most challenging frontiers in theoretical physics. It requires combining our understanding of quantum mechanics, general relativity, and many-body physics in ways that push the limits of current mathematical techniques. But the potential insights could be profound. offering new perspectives on the nature of space-time itself and the fundamental laws that govern the universe. Back on Earth, the practical applications of time crystal research continue to expand in unexpected directions. Engineers are exploring whether these temporal structures could revolutionize our approach to energy storage and distribution. Traditional batteries store energy in chemical bonds or electric fields, but time crystals suggest the possibility of storing energy in temporal patterns themselves. Imagine a power grid where energy is stored not in massive battery farms or pumped hydroelectric systems, but in networks of time crystals that maintain their charge through crystallized temporal patterns. Such systems might be incredibly efficient, losing no energy to heat or other forms of dissipation because the storage mechanism operates in the temporal domain rather than through conventional physical processes. The development of time crystal energy storage faces significant technical challenges, of course. Current time crystals operate at extremely low temperatures and in carefully controlled environments that are far from the robust, room temperature systems needed for practical energy applications. But the fundamental physics suggest that these limitations might not be insurmountable. Recent theoretical work has explored the possibility of high-temperature time crystals, systems that could maintain their temporal crystalline structure even under the messy, noisy conditions of real-world applications. These warm time crystals might be protected by topological properties that make them resistant to thermal fluctuations, or they might harness the thermal noise itself as part of their organizational mechanism. The search for room temperature time crystals has become an active area of research, with scientists exploring everything from exotic magnetic materials to specially designed metamaterials that could support temporal crystallization under ambient conditions. The discovery of such systems could transform not just energy storage, but our entire relationship with time and temporal organization. In the field of quantum computing, time crystals are opening new possibilities for creating quantum memories that could store and process information for indefinite periods without any external power source. Current quantum computers struggle with decoherence, the tendency for quantum information to degrade over time as the system interacts with its environment. Time crystals offer a potential solution, providing a way to encode quantum information in temporal patterns that are naturally resistant to environmental perturbations. Researchers are developing quantum algorithms specifically designed to take advantage of time crystal properties. These algorithms could solve certain types of problems more efficiently than conventional quantum computers by using the temporal structure of time crystals to perform calculations that unfold over time rather than through spatial quantum gates. The intersection of time crystals and artificial intelligence represents another exciting frontier. Machine learning algorithms that operate on temporal data, such as those used for speech recognition or time series prediction, might benefit from time crystal-inspired architectures that can maintain long-term temporal dependencies without the memory limitations that plague current neural networks. Some researchers are exploring whether artificial neural networks could be designed to exhibit time crystal-like behavior, creating AI systems with perfect temporal memory that could learn from experiences across arbitrarily long time spans. Such systems might be particularly useful for applications requiring long-term planning or the integration of information across extended periods. The study of time crystals has also begun to influence fields as diverse as biology, chemistry, and materials science. Chemists are investigating whether certain chemical reactions might exhibit time crystal-like behavior, maintaining oscillatory patterns that persist indefinitely without external driving forces. Such reactions could lead to new forms of chemical synthesis or energy conversion that operate with unprecedented efficiency. Biologists are examining whether time crystal principles might explain some of the remarkable temporal precision observed in living systems. From the circadian rhythms that govern sleep and wakefulness, to the precisely timed developmental programs that guide embryonic growth, biological systems exhibit temporal organization that seems to transcend what should be possible given the noisy, chaotic nature of cellular biochemistry. The possibility that life itself might employ time crystal-like mechanisms raises profound questions about the relationship between physics and biology. If temporal crystallization is a fundamental property of complex quantum systems, it might be one of the physical principles that made the evolution of life possible in the first place. Materials scientists are working to create new substances that exhibit time crystal properties, engineering atomic and molecular structures that can support temporal crystallization. These designer time crystals might have applications in everything from precision sensing to quantum communication, offering new ways to manipulate and control temporal patterns for technological purposes. The development of time crystal materials requires pushing the boundaries of what's possible in materials synthesis. Researchers must learn to control not just the spatial arrangement of atoms and molecules, but their temporal organization as well. This represents a new frontier in materials science, where the fourth dimension of time becomes another degree of freedom that can be engineered and optimized. As we continue our gentle exploration of these remarkable systems, we begin to see that time crystals are more than just exotic laboratory curiosities. They represent a fundamental expansion of our understanding of what matter can do, how time behaves, and what kinds of order are possible in the quantum world. They hint at deeper truths about the nature of reality itself, suggesting that the universe might be far more rhythmic, far more organized in time than our everyday experience would suggest. The philosophical implications of time crystals continue to unfold as our understanding deepens. These systems challenge our basic assumptions about time, causality, and the relationship between order and entropy. They suggest that time might not be the smooth, featureless dimension we once imagined, but rather a rich, structured medium capable of supporting its own forms of crystalline organization. Some philosophers of science have begun to argue that time crystals represent a new kind of existence, one that transcends the traditional categories of being and becoming. These systems exist in a state of pure temporal being, maintaining their identity through rhythm rather than through spatial persistence. They are what they do, existing primarily through their temporal patterns rather than through any fixed material substrate. This temporal mode of existence might offer new insights into some of the deepest questions in philosophy and physics. What does it mean to exist? How do patterns persist through time? What is the relationship between identity and change? Time crystals, in their quiet way, are beginning to suggest new answers to these ancient questions. As research continues, we're discovering that the universe of time crystals is far richer and more varied than anyone initially imagined. There are discrete time crystals that tick with clockwork precision, continuous time crystals that flow like temporal rivers, and hybrid systems that exhibit both types of behavior simultaneously. There are time crystals that maintain rigid temporal order, and others that allow for controlled temporal chaos. Some time crystals exist in isolation, maintaining their temporal patterns independently of their surroundings. Others form vast networks, creating collective temporal behaviors that span multiple systems. And still others seem to exist in a kind of temporal superposition, maintaining multiple temporal patterns simultaneously until some measurement or interaction forces them to choose a single temporal state. The taxonomy of time crystals continues to grow as researchers discover new varieties and new forms of temporal organization. Each new type reveals different aspects of how matter can organize itself in time, adding new chapters to the emerging story of temporal crystallization. Tonight, as you settle into the gentle rhythm of approaching sleep, perhaps you can sense the profound beauty of these temporal structures that surround us. In laboratories around the world, time crystals are ticking away their perfect patterns, adding their quiet music to the symphony of quantum reality that underlies all existence. They remind us that the universe is far stranger and more wonderful than we ever dared imagine, filled with hidden rhythms and temporal architectures that we're only beginning to understand. These remarkable systems whisper to us about the deep connections between time, matter, and consciousness, suggesting that reality itself might be fundamentally rhythmic in nature. They hint at the possibility that time is not just the stage upon which the drama of existence unfolds, but an active participant in that drama, capable of crystallizing into patterns as beautiful and enduring as any structure we find in space. The story of time crystals reminds us that discovery often comes when we least expect it, when we're willing to ask questions that seem impossible, and then spend years patiently working to answer them. These temporal structures emerge from the intersection of theoretical audacity and experimental precision, proving once again that the universe delights in exceeding our wildest expectations. As we drift deeper into understanding these remarkable systems, we encounter what might be their most profound gift to science. They're teaching us to think about time in entirely new ways. For centuries, we've treated time as a backdrop, a stage upon which the real action of physics takes place. But time crystals suggest that time itself might be an active participant, capable of forming structures as complex and beautiful as any cathedral or snowflake. This shift in perspective is beginning to influence how we approach some of the most challenging problems in modern physics. Consider the puzzle of quantum gravity, the long-sought theory that would unite Einstein's general relativity with the principles of quantum mechanics. Traditional approaches have focused primarily on the spatial aspects of this unification, trying to understand how space itself becomes quantized at the smallest scales. But time crystals suggest that we might also need to consider the temporal dimension more carefully. If time can crystallize, if it can form organized patterns and structures, then perhaps the quantum nature of space-time involves not just the granularity of space, but the rhythmic organization of time itself. It's a speculative idea, but one that's beginning to capture the imagination of theoretical physicists around the world. The mathematics of quantum gravity with temporal crystallization would be extraordinarily complex, involving concepts from algebraic topology, category theory, and dynamical systems theory. But the basic intuition is elegant. Just as space might be made of discrete, quantized units at the Planck scale, time might be organized into crystalline patterns that give structure to the temporal dimension of reality. Some researchers have begun to explore whether the expansion of the universe itself might involve a kind of cosmic time crystal, a vast temporal structure that governs how space-time evolves over cosmological timescales. This cosmic time crystal would be unimaginably large, its temporal patterns playing out over billions of years, but its basic principles might be similar to those we observe in tabletop experiments. The idea that the universe itself might be a time crystal has profound implications for our understanding of cosmic evolution. It suggests that the expansion of space and the flow of time might not be smooth and continuous, as we typically assume, but rather organized into discrete temporal phases that repeat over vast scales. Such organization might help explain some of the mysterious features of our cosmos, from the uniformity of the cosmic microwave background to the accelerating expansion driven by dark energy. Meanwhile, in the more immediate realm of technology, time crystals are beginning to find applications that seemed like pure fantasy just a few years ago. Engineers are developing time crystal oscillators that could serve as the ultimate reference clocks, maintaining their temporal patterns with a precision that surpasses even the best atomic clocks currently available. These temporal oscillators work by harnessing the natural rhythm of time crystals rather than relying on the vibrations of atoms or the decay of radioactive nuclei. Because time crystals maintain their patterns through quantum mechanical principles rather than classical dynamics, they're potentially immune to many of the environmental factors that limit the precision of conventional timepieces. Imagine navigation systems that rely on time crystal clocks so precise they could detect the tiny gravitational time dilation effects caused by driving up a small hill, or communication networks that use time crystal synchronization to coordinate signals across vast distances with unprecedented accuracy. The applications seem limited only by our imagination and our ability to create time crystals that operate under practical conditions. The development of portable time crystals represents one of the most significant engineering challenges in the field. Current laboratory time crystals require elaborate cooling systems, ultra-high vacuum chambers, and carefully controlled electromagnetic environments. Creating time crystals that could operate in a smartphone or a car requires finding ways to maintain temporal crystallization under far less ideal conditions. Recent progress in this direction has focused on discovering new types of time crystals that are naturally more robust against environmental perturbations. Some researchers are investigating biological inspirations, looking at how living systems maintain precise temporal organization despite operating in warm, noisy environments. Others are exploring whether certain materials might naturally support time crystal behavior at room temperature. The search for room temperature time crystals has led to some unexpected discoveries. Researchers have found hints of temporal crystallization in systems as diverse as superconducting circuits, magnetic materials, and even certain types of glass. While none of these systems exhibit the perfect temporal order of laboratory time crystals, they suggest that temporal crystallization might be more common in nature than we initially realized. One particularly intriguing development is the discovery of what researchers call pseudo-time crystals, systems that exhibit time crystal-like behavior for extended periods, before eventually thermalizing and losing their temporal organization. These systems aren't true time crystals in the strictest sense, but they could be practically useful for applications that don't require infinite temporal coherence. The study of pseudo-time crystals has revealed new insights into the relationship between temporal order and thermodynamics. These systems seem to exist in a kind of temporal purgatory, neither achieving perfect time crystal order nor completely dissolving into thermal chaos. They maintain their patterns for minutes, hours, or even days before succumbing to the inevitable increase of entropy. Understanding what determines the lifetime of pseudo-time crystals could lead to strategies for extending their temporal coherence, potentially creating systems that maintain time crystal-like behavior for practically useful periods without requiring the extreme conditions needed for true time crystals. The intersection of time crystals and artificial intelligence has opened yet another fascinating avenue of research. Machine learning algorithms that can maintain perfect temporal memory could revolutionize how we approach problems involving time series data, from weather prediction to financial modeling to speech recognition. Traditional neural networks struggle with what researchers call the vanishing gradient problem, where information from the distant past gradually fades away as the network processes new inputs. Time crystal-inspired architectures could potentially overcome this limitation by encoding information in temporal patterns that persist indefinitely without degradation. Researchers are developing new types of artificial neurons that exhibit time crystal-like behavior, maintaining oscillatory patterns that can encode and store information across arbitrary timescales. These temporal neurons could form the building blocks of AI systems with unprecedented capabilities for long-term learning and memory. The philosophical implications of time crystal artificial intelligence are profound. If consciousness emerges from temporal patterns in neural activity, then AI systems based on time crystal principles might be taking a significant step toward more human-like forms of awareness and understanding. Some researchers have speculated about the possibility of time crystal consciousness, forms of artificial awareness that exist primarily in the temporal domain rather than being localized to specific spatial structures. Such consciousness might experience time very differently than we do, existing as patterns of organized duration rather than as spatially defined entities moving through time. The ethics of creating time crystal-based AI systems raise important questions that we're only beginning to consider. If these systems can maintain perfect memory across indefinite time spans, what are our obligations regarding their experiences and well-being? How do we ensure that artificial minds with temporal crystalline structures are treated with appropriate respect and consideration? As time crystal research continues to mature, we're beginning to see the emergence of what some scientists call temporal engineering, the deliberate design and manipulation of temporal structures for specific purposes. This new field combines insights from time crystal physics with techniques from materials science, electrical engineering, and computer science to create systems with precisely controlled temporal properties. Temporal engineers work with time in much the same way that traditional engineers work with space and materials. They design temporal architectures, optimize temporal performance, and solve temporal engineering problems. It's a new way of thinking about design and construction, one that treats time as a medium that can be shaped and molded to achieve desired outcomes. The tools of temporal engineering are still in their infancy, but they're developing rapidly. Researchers are creating computer simulations that can model complex temporal structures, design algorithms that can optimize temporal patterns, and experimental techniques that can fabricate time crystals with precisely specified properties. One of the most exciting developments in temporal engineering is the creation of programmable time crystals, systems whose temporal patterns can be dynamically reconfigured through external control signals. These systems could serve as the basis for temporal computers, machines that perform calculations not through spatial logic gates, but through carefully orchestrated temporal patterns. Imagine a computer where each calculation unfolds over time, with different temporal patterns corresponding to different mathematical operations. Such machines might be particularly well suited for problems involving time series analysis, dynamical systems, or any application where the temporal evolution of the solution is as important as the final result. The development of temporal programming languages represents another frontier in this emerging field. These languages would allow programmers to specify not just what they want a system to compute, but when and how the computation should unfold over time. The syntax of such languages would need to capture temporal relationships and dependencies in ways that conventional programming languages cannot. Early experiments in temporal programming have focused on simple tasks like creating specific rhythmic patterns or coordinating the timing of multiple time crystal systems. But researchers envision much more sophisticated applications, from temporal databases that store information in crystallized time to temporal operating systems that manage computational resources across multiple temporal dimensions. The convergence of time crystal physics with information theory has led to some particularly elegant insights about the nature of information itself. Traditional information theory treats information as static entities that can be stored, transmitted, and processed. But time crystals suggest that information might also have temporal structure, existing not just as patterns in space, but as patterns in time. This temporal information theory is still in its early stages, but it's already yielding interesting results. Researchers have shown that certain types of information can be more efficiently encoded in temporal patterns than in spatial ones, and that time crystal systems can perform certain types of information processing tasks with greater efficiency than conventional computers. The concept of temporal entropy, the amount of disorder in a temporal pattern, has emerged as a key tool for understanding how information can be organized in time. Just as spatial entropy measures the randomness of spatial arrangements, temporal entropy measures the predictability of temporal sequences. Time crystals, with their perfect temporal order, represent states of minimal temporal entropy. Understanding how to manipulate temporal entropy could lead to new forms of data compression, error correction, and information storage that operate in the temporal domain. These techniques might be particularly useful for applications involving streaming data, real-time processing, or any situation where the temporal structure of information is as important as its content. As we near the completion of our gentle journey through the world of time crystals, we find ourselves at the threshold of a new age in science and technology. These remarkable systems have shown us that the universe is capable of organizing itself in ways we never imagined, creating structures that exist primarily in time rather than space. The story of time crystals is ultimately a story about the power of human curiosity and ingenuity. It began with a simple question about whether matter could crystallize in time, and it has blossomed into an entire field of research that's transforming our understanding of physics, technology, and perhaps even consciousness itself. These temporal architects have taught us to see time not as an empty container, but as a rich medium capable of supporting its own forms of organization and structure. They've shown us that the universe is more musical, more rhythmic than we ever dared imagine, filled with temporal melodies that play out across scales from the quantum to the cosmic. As you settle into the peaceful rhythm of approaching sleep, perhaps you can sense these time crystals ticking away their perfect patterns in laboratories around the world. They remind us that even in a universe governed by uncertainty and change, there can be islands of perfect temporal order, oases of crystallized time where rhythm and pattern persist against all odds. The future of time crystal research stretches out before us like an uncharted ocean of possibilities. Each new discovery reveals additional mysteries. Each technological breakthrough opens new applications, and each theoretical insight deepens our understanding of the fundamental nature of reality itself. Tonight, as you drift toward dreams, know that you've been witness to one of the most remarkable discoveries in modern physics. Time crystals have shown us that the universe is far stranger and more beautiful than we ever imagined, filled with hidden temporal architectures that dance to rhythms as old as time itself and as new as tomorrow's experiments. In the quiet depths of quantum reality, these temporal structures continue their eternal dance, adding their perfect rhythms to the symphony of existence that surrounds us all. They whisper to us about the deep connections between time, matter, and consciousness, reminding us that we live in a universe where even time itself can crystallize into patterns of extraordinary beauty and precision. Sweet dreams, fellow traveler in the realm of scientific wonder. May your rest be as peaceful and perfectly timed as the gentle oscillations of a time crystal, ticking away its eternal rhythm in the quantum depths of our extraordinary universe. As we find ourselves in the gentle twilight of our exploration, there's one more aspect of time crystals that deserves our quiet contemplation tonight. It's perhaps the most poetic aspect of all, the way these remarkable structures seem to bridge the gap between the abstract mathematics of theoretical physics and the lived experience of consciousness itself. You see, time crystals exist in a realm that feels almost magical, where the rigid determinism of physical law meets something that seems to approach free will. They make choices, in a sense, selecting their own temporal rhythms from an infinite array of possibilities. When we drive them with our carefully timed pulses, they don't simply respond mechanically like clockwork. Instead, they seem to listen to our rhythm and then decide to dance to their own beat, choosing patterns that are related to but distinct from what we offer them. This capacity for what we might call temporal autonomy has profound implications that ripple far beyond the laboratory. Consider how it changes our understanding of determinism itself. In the classical view of physics, if you know the initial conditions of a system perfectly and understand all the forces acting upon it, you can predict its future behavior with absolute certainty. The universe, in this view, is like a vast clockwork mechanism where every tick follows inevitably from the previous one. But time crystals suggest a more nuanced picture. Even when we control their environment precisely, even when we know their quantum state exactly, they still maintain a kind of temporal sovereignty, choosing their own rhythmic patterns from the quantum mechanical possibilities available to them. It's not randomness, exactly, but something more subtle, a form of order that emerges from the interplay between external driving forces and internal quantum dynamics. This emergence of temporal autonomy from quantum mechanics has captured the attention of philosophers and neuroscientists studying consciousness. Some researchers have begun to wonder whether the sense of temporal flow that characterizes conscious experience might arise from similar principles. After all, our awareness seems to have its own rhythm, its own capacity to organize experience into meaningful temporal patterns that don't simply mirror the external world. When you close your eyes and let your mind wander, you might notice that your thoughts don't follow a mechanical sequence. Instead, they seem to drift and flow according to their own internal logic, creating patterns of association and memory that feel both spontaneous and somehow inevitable. This temporal organization of consciousness might share deep similarities with the way time crystals organize their quantum states into coherent temporal patterns. The mathematics describing both phenomena involves similar concepts, networks of interacting components that somehow achieve collective temporal coordination without any central controlling mechanism. In time crystals, it's quantum spins or atomic states that synchronize their temporal evolution. In consciousness, it might be neural networks that coordinate their firing patterns to create the unified stream of awareness. Of course, the brain operates under vastly different conditions than laboratory time crystals. Neural systems are warm, noisy, and constantly changing, far from the pristine quantum environments where artificial time crystals thrive. But evolution has had billions of years to discover ways of creating temporal order under these challenging conditions, and the results might involve principles that we're only now beginning to understand through time crystal research. Some neuroscientists have begun to investigate whether certain brain rhythms might exhibit time crystal-like properties. The alpha waves that appear when we close our eyes, for instance, maintain remarkably stable frequencies, even as the brain's overall activity changes dramatically. These rhythms seem to persist independently of external stimulation, creating a kind of temporal scaffolding that might be essential for conscious experience. The gamma oscillations associated with conscious awareness show even more intriguing properties. These high-frequency rhythms appear to coordinate activity across different regions of the brain, binding together diverse sensory inputs and memories into unified conscious experiences. They maintain their temporal organization even when the content of consciousness changes, suggesting a form of temporal stability that transcends the specific information being processed. Recent experiments using advanced brain imaging techniques have revealed that these neural rhythms exhibit some surprisingly time crystal-like behaviors. They can maintain their patterns independently of external stimulation, they show remarkable stability against perturbations, and they seem to coordinate their timing across vast networks of brain regions without any obvious controlling mechanism. The possibility that consciousness involves time, crystal-like phenomena raises profound questions about the nature of subjective experience. If our sense of temporal flow emerges from quantum mechanical processes similar to those in time crystals, what does this tell us about free will, personal identity, and the relationship between mind and matter? These questions push us toward a deeper understanding of how physical processes give rise to the inner life of the mind. Time crystals suggest that temporal organization might be far more fundamental to the universe than we previously realized, perhaps providing the foundation for phenomena as diverse as quantum coherence, biological rhythms, and conscious awareness itself. The study of time crystals has also begun to influence our understanding of memory, that most temporal of cognitive phenomena. Memories, after all, are patterns that persist through time, maintaining their structure across days, years, and even decades despite the constant turnover of molecules in our brains. How do these temporal patterns maintain their coherence in the face of biological noise and change? Time crystals offer a potential answer. Their ability to maintain temporal patterns indefinitely, protected by quantum mechanical principles rather than classical stability, suggests new ways of thinking about how information can be preserved across time. Perhaps memories are encoded not just in the spatial patterns of neural connections, but in temporal patterns that exhibit time crystal-like stability. This temporal theory of memory could help explain some of the mysterious features of human recollection. Why do some memories remain vivid for decades, while others fade within days? Why can certain experiences, particularly emotional ones, seem to crystallize in memory with perfect clarity? The answer might lie in the temporal crystallization of neural activity patterns, creating memories that are as stable and enduring as time crystals themselves. The implications extend beyond individual memories to the broader question of how personal identity persists through time. We feel like the same person from day to day, despite the fact that our bodies are constantly changing at the cellular and molecular level. This sense of temporal continuity might arise from time crystal-like patterns in neural activity that maintain their structure across the constant flux of biological processes. As we contemplate these profound connections between time crystals and consciousness, we begin to see that these quantum structures might hold keys to some of the deepest mysteries of existence. They suggest that the universe might be fundamentally temporal in nature, organized not just through spatial relationships but through patterns that unfold in time itself. The search for time crystals in biological systems has become an active area of research, with scientists investigating everything from circadian rhythms to neural oscillations to the precisely timed chemical reactions that drive cellular metabolism. While we haven't yet found perfect biological time crystals, the principles underlying temporal crystallization might be operating throughout the living world in forms we're only beginning to recognize. Some researchers have proposed that evolution itself might favor systems that can maintain temporal organization, leading to the emergence of biological rhythms that share fundamental properties with time crystals. The 24-hour cycles that govern sleep and wakefulness, the seasonal patterns that drive migration and reproduction, the millisecond precise timing of neural communication, all of these might represent different manifestations of the same underlying principles that create time crystals in quantum systems. The possibility that life itself might be fundamentally temporal in nature, organized around principles of temporal crystallization, suggests new ways of thinking about biology, medicine, and our relationship with the natural world. If our bodies are networks of interacting temporal patterns, then health and disease might be understood in terms of temporal harmony and discord, with medical treatments designed to restore the natural rhythmic patterns that keep us alive and well. This temporal view of biology has already begun to influence medical research. Chronotherapy, the practice of timing medical treatments to align with the body's natural rhythms, has shown remarkable success in treating conditions ranging from cancer to depression. By working with the temporal patterns of biological systems rather than against them, doctors can achieve better outcomes with fewer side effects. The field of circadian medicine has revealed that almost every aspect of physiology follows temporal patterns, from hormone levels to immune function to the way our bodies process medications. These patterns aren't just responses to external light cycles, they're generated internally by molecular clockwork that exhibits some intriguing similarities to time crystal behavior. The molecular mechanisms underlying circadian rhythms involve feedback loops where certain genes turn each other on and off in precisely timed sequences. These genetic oscillators maintain their rhythmic patterns, even in the absence of external cues, much like time crystals maintaining their temporal organization without external energy input. Recent discoveries in circadian biology have revealed that these molecular clocks exist not just in specialized brain regions, but in virtually every cell in our bodies. Each cell maintains its own internal timekeeper, and somehow these billions of cellular clocks coordinate their activity to create the unified temporal patterns we observe at the level of the whole organism. This cellular timekeeping might involve quantum mechanical processes that share fundamental similarities with time crystal formation. The precise molecular interactions that drive circadian oscillations operate at scales where quantum effects become important, and some researchers have begun to investigate whether quantum coherence might play a role in maintaining the stability of biological rhythms. The idea that quantum mechanics might be essential for life has gained increasing support in recent years. Photosynthesis, for instance, appears to use quantum coherence to achieve nearly perfect efficiency in capturing solar energy. Bird navigation might rely on quantum entanglement in specialized proteins. And now, time crystal research suggests that quantum temporal organization might be crucial for maintaining the rhythmic patterns that coordinate biological processes. These discoveries are revolutionizing our understanding of the relationship between physics and biology. Rather than being separate domains governed by different principles, quantum physics and biology might be intimately connected, with life representing one of the most sophisticated applications of quantum mechanics in the known universe. As we drift toward the conclusion of our gentle journey through the world of time crystals, we find ourselves changed by the experience. These remarkable structures have shown us that time is not the empty, featureless dimension we once imagined, but a rich medium capable of supporting its own forms of organization and beauty. They've taught us that the universe is more musical than we ever dared dream, filled with temporal rhythms that play out across scales from the quantum to the cosmic. They've suggested new connections between physics and consciousness, between quantum mechanics and biology, between the abstract mathematics of many body systems and the lived experience of temporal awareness. Perhaps most importantly, time crystals have reminded us that the universe is endlessly creative, always capable of surprising us with new forms of order and organization that exceed our wildest expectations. They represent a triumph of human curiosity and ingenuity, proving once again that the most beautiful discoveries often emerge when we're brave enough to ask seemingly impossible questions. The story of time crystals is far from over. Each new experiment reveals additional mysteries. Each theoretical advance opens new questions, and each potential application hints at possibilities we've only begun to imagine. These temporal structures have opened a new chapter in our understanding of reality, one that will undoubtedly continue to unfold in ways we cannot yet anticipate. Tonight, as you settle into the peaceful rhythm of approaching sleep, perhaps you can sense the profound beauty of these temporal patterns that surround us. In laboratories around the world, time crystals are maintaining their perfect rhythms, adding their quiet music to the symphony of quantum reality that underlies all existence. They whisper to us about the deep connections between time, matter, and consciousness, suggesting that we live in a universe where even duration itself can crystallize into structures of extraordinary precision and beauty. They remind us that reality is far stranger and more wonderful than our everyday experience suggests, filled with hidden architectures that exist primarily in time rather than space. As you drift toward dreams, know that you carry with you the knowledge of these remarkable discoveries. Time crystals have shown us that the universe is not just a collection of objects moving through empty time, but a vast network of temporal patterns, rhythmic structures, and crystallized durations that dance together in ways we're only beginning to understand. Sleep well, fellow explorer of the temporal frontier. May your rest be as peaceful and perfectly timed as the gentle oscillations of a time crystal, ticking away its eternal rhythm in the quantum depths of our extraordinary musical universe. And may your dreams be filled with the wonder of discovering that time itself can crystallize into patterns as beautiful and enduring as the most perfect snowflake or the most elegant mathematical theorem. In the quiet darkness of night, these temporal architects continue their endless dance, keeping perfect time in a universe that has revealed itself to be far more rhythmic, far more organized, far more alive with temporal music than we ever imagined possible. The gentle rhythm of time crystals brings us to a profound realization as we drift toward the end of our peaceful exploration tonight. These remarkable structures have revealed something extraordinary about the nature of existence itself, something that touches the very core of what it means to be conscious beings moving through the flowing river of time. You see, time crystals represent more than just a new phase of matter or an exotic quantum phenomenon. They embody a fundamental truth about the universe that we're only now beginning to appreciate. In a cosmos that seems to favor chaos over order, where entropy steadily increases and systems naturally drift toward disorder, time crystals stand as beacons of hope, demonstrating that perfect temporal organization can emerge and persist even in the face of quantum uncertainty. This persistence of order in time mirrors something deeply familiar to us as conscious beings. Our own experience of awareness flows through time with remarkable continuity, creating coherent narratives from the constant flux of sensation, memory, and thought. Just as time crystals maintain their temporal patterns through quantum mechanical principles, our consciousness seems to maintain its coherence through mechanisms we're only beginning to understand. The mathematics that describe time crystals are elegant in their simplicity, yet profound in their implications. These equations tell us that temporal organization isn't just possible but inevitable under certain conditions. When quantum systems reach the right balance between order and chaos, between driving and resistance, temporal crystallization emerges as naturally as frost forms on a window or waves appear on a beach. This inevitability suggests that time crystals might be far more common in the universe than we currently realize. Perhaps they exist in forms we haven't yet learned to recognize, hidden in the quantum depths of materials around us, in the precise timing of biological processes, or even in the vast cosmic structures that organize matter on the larger scales. The search for naturally occurring time crystals has become a quest that spans from the smallest quantum systems to the grandest cosmic phenomena. Researchers are investigating whether certain minerals might harbor temporal crystalline phases, whether living systems employ time crystal-like mechanisms to maintain their biological rhythms, and whether the universe itself might exhibit temporal crystalline behavior on cosmological scales. Each potential discovery opens new questions about the role of temporal organization in shaping reality. If time crystals are indeed fundamental features of the quantum world, they might help explain some of the deepest mysteries in physics, from the arrow of time to the nature of consciousness to the fine-tuned constants that allow complexity to emerge in our universe. The technological applications of time crystal research continue to expand in directions that seemed like pure fantasy just a few years ago. Engineers are developing temporal sensors that can detect minute changes in time's flow, quantum computers that store information in crystallized duration, and communication systems that encode messages in temporal patterns rather than electromagnetic waves. These applications hint at a future where we don't just move through time but actively shape it, creating temporal architectures as deliberately as we now build bridges or design circuits. The emerging field of temporal engineering promises to revolutionize how we think about technology, computation, and our relationship with the dimension of duration itself. But perhaps the most beautiful aspect of time crystal research is how it has changed our relationship with time. These structures have taught us to see time not as an adversary that ages us and limits us, but as a collaborator in the grand project of existence. Time, we now understand, isn't just the medium through which change occurs, it's an active participant in creating the patterns and structures that make life and consciousness possible. The philosophical implications ripple outward like waves in a temporal pond. If time can crystallize, if duration itself can form organized structures, then perhaps our experience of temporal flow is just one manifestation of a deeper temporal reality that exists beyond our direct perception. We might be like observers watching the surface of an ocean, seeing only the waves while remaining unaware of the vast currents and structures that exist beneath. This deeper temporal reality might hold keys to some of our most profound questions. Why do we experience time as flowing from past to future? How does consciousness maintain its continuity across the constant flux of neural activity? What is the relationship between subjective time and the time measured by our clocks and equations? Time crystals whisper possible answers to these ancient puzzles. They suggest that temporal flow might emerge from underlying temporal structures, that consciousness might be a form of temporal crystallization in neural networks, and that subjective time might be as real and fundamental as the objective time of physics. As we continue to explore these possibilities, we're discovering that time crystals have gifts to offer beyond their scientific and technological applications. They provide a new way of thinking about persistence and change, about order and chaos, about the relationship between individual components and collective behavior. They teach us that stability doesn't require stasis, that perfect order can coexist with constant motion, and that the most beautiful patterns often emerge at the boundary between predictability and surprise. These lessons extend far beyond the laboratory. In our daily lives, we can find inspiration in the way time crystals maintain their integrity while embracing change. Like these quantum structures, we can learn to find our own rhythms, to maintain our essential patterns while adapting to the constant flux of experience. We can discover ways to create temporal harmony in our schedules, our relationships, and our inner lives. The study of time crystals has also revealed the importance of driving forces in maintaining temporal organization. Just as time crystals require periodic external pulses to sustain their patterns, we too benefit from regular rhythms and routines that help organize our experience in time. The gentle pulsing of day and night, the weekly cycles of work and rest, the seasonal rhythms of growth and dormancy, all of these provide the temporal scaffolding that helps us maintain our own forms of life organization. Understanding this connection between external rhythms and internal organization has practical implications for how we structure our lives. By aligning our activities with natural temporal patterns, we can achieve greater harmony and efficiency. This wisdom has been known to traditional cultures for millennia, but time crystal research is now providing a scientific foundation for these ancient insights. The medical applications of temporal understanding continue to expand as researchers develop new approaches to health and healing based on temporal principles. Chronotherapy has evolved from a specialized field to a mainstream medical approach, with treatments timed to work with the body's natural rhythms rather than against them. Some researchers are investigating whether certain diseases might involve disruptions in the body's temporal organization, suggesting new therapeutic approaches based on restoring natural temporal patterns. The connection between time crystals and health extends beyond medicine to encompass our overall relationship with time and well-being. Learning to live in harmony with temporal rhythms, to create healthy patterns in our daily lives, and to find balance between activity and rest can improve both physical health and mental well-being. Time crystals teach us that perfect organization doesn't require rigid control, but rather the right balance of structure and flexibility. As we near the gentle conclusion of our journey tonight, we find ourselves enriched by our exploration of these remarkable temporal structures. Time crystals have shown us that the universe is far more organized, far more musical, far more alive with temporal beauty than we ever imagined. They've revealed connections between quantum mechanics and consciousness, between physics and philosophy, between the smallest scales of reality and the largest questions of existence. These discoveries remind us that science is fundamentally about wonder, about pushing beyond the boundaries of what we think we know and finding new marvels hidden in the fabric of reality. Time crystals emerged from the intersection of theoretical curiosity and experimental creativity, proving once again that the universe delights in exceeding our expectations. The story of time crystals is ultimately a story about the power of asking impossible questions. When Frank Wilczek first wondered whether matter could crystallize in time, many scientists thought the idea was intriguing, but probably impossible. Today, time crystals are reality, opening new frontiers in physics, technology, and our understanding of existence itself. This reminds us that the impossible questions often lead to the most beautiful discoveries. By daring to imagine what seems unthinkable, by pursuing ideas that challenge our fundamental assumptions, we open ourselves to the possibility of finding wonders we never knew existed. Tonight, as you settle into the peaceful rhythm of approaching sleep, perhaps you can sense these time crystals maintaining their perfect temporal patterns in laboratories around the world. They tick away their eternal rhythms like cosmic metronomes, keeping time for a universe that has revealed itself to be far more organized, far more beautiful than we ever dared hope. These temporal architects whisper to us about the deep structures of reality, about the hidden music that flows through the quantum depths of existence. They remind us that we live in a universe where even time itself can crystallize into patterns of extraordinary precision and beauty, where duration can become as organized and structured as the most perfect snowflake or the most elegant mathematical proof. As you drift toward dreams, carry with you the wonder of these discoveries. Time crystals have shown us that reality is far stranger and more beautiful than our everyday experience suggests, filled with temporal architectures that exist primarily in the dimension of when rather than where. They've revealed that the universe is not just a collection of objects moving through empty time, but a vast symphony of temporal patterns, rhythmic structures, and crystallized durations that dance together in perfect harmony. Sleep well, dear traveler, in the realm of temporal wonder. May your rest be as peaceful and perfectly timed as the gentle oscillations of these quantum structures, and may your dreams be filled with the music of crystallized time flowing through the very fabric of our extraordinary universe. In the quiet darkness, time crystals continue their eternal dance, adding their perfect rhythms to the cosmic symphony that surrounds us all, reminding us that time itself is alive with beauty, organization, and infinite possibility.